All right, so this says 1 and 2 because it used to be 2 lectures, which is just brutal. And so I put everything together in one slide set, and this is really only kind of the second half of the semester. So don't let the size of it throw you too much. There's really, more information here than anybody can cover in one lecture. So I'm going to skip over stuff that's not on the final exam. And so if you download the PDFs, you'll see what I'm going to be skipping over because those slides are grayed out. But so in other words, if not the PDF, the PowerPoint slides. So you'll see what I'm not covering, but if you want to download the PowerPoint slides, you can kind of see it later on. The PDF's unfortunately going to show you everything because they automatically convert and show the hidden slides. I thought they didn't, but so anyway, another short answer is it's not quite as long as it looks, but we do have a bit to cover. So I will have everything available by Friday noon with the answers provided. So auto-corrected answers won't be there until Friday, which you probably haven't seen that in a while. You'll see it on the practice exam. And so there's probably going to be a little bit of work for me to do to get all of the essay parts graded. So I don't think I'll have the essay parts graded by Friday, but the automated answers should be available on Friday. The practice exam, sorry, I'm on the practice exam here. Those things will not be auto-corrected ever. So I won't have auto-corrected answers for you or essay answers for you on the practice exam. That's kind of what that's all about. This is not true. There's really only about 25 questions on the practice exam. Sorry about that. And 3 essay questions. I will have that for you as soon as possible tomorrow morning so you can look at the essay. That's probably what everybody's most curious about because the rest of these things you've seen in your quiz questions. So bear with me while I try to, polish that up and reduce any chance of confusion and errors. Essentially, it's going to represent the, maybe I'd say a modestly small homework assignment. So there will be a somewhat sophisticated data structure. Think of something on the order of maybe a jigsaw puzzle, maybe. And so you're going to need to deal with some pointers, and you're going to need to deal with some classes and some methods and some initializations, and really most of the stuff that we've seen a little bit of class hierarchy stuff. So chess will help you on that as well. The good news is you'll see an example of that kind of problem tomorrow, and you'll have a chance to kind of get used to it before you see the final version of it on the test on Tuesday. So that's kind of what we got in front of us. Let me see if there's anything else before we dive in. Right, so 540, I think at some point I told you 610. That was from last year. It's changed. So please write that time down. Be here at 540. And I will have more information for you on this part of it tomorrow. Okay. So by the way, I am encouraging people to, if they want, to work in something like a Replit or Program IZ and submit a link. You can also upload and submit, or you can't upload into Canvas, but you can submit your code for the problem. So I would say choose your strategy early, and maybe find something that you're comfortable working in. If you want to work in VS Code or something else, that's fine, but you will then, of course, have to paste all that code in at the end. It's probably not more than maybe 100 lines of code at the end, not even probably that. So you're not pasting a lot of material, but you might find it easier to just work in a link while you're working and then submit that. So you'll have a choice to do that. Okay, so part 1 and part 2, they're kind of spread out, and we're going to be skipping a lot of slides in here, so it's not as bad, quite as bad as it sounds. But why don't we just dive in on the stuff and see how far we can get. Part 1 topics kind of cover all of this stuff. Again, some of it's grayed out, but I'll kind of go over the stuff that will be on the final exam. All of these things are useful and important. So if you ever have to come back and brush up on your C++ advanced stuff, this is probably a good slide set to test yourself out on. Quick review, a very large part of C++ is the container classes that we were introduced to kind of early in the second half of the semester. So container classes are things like vectors and strings. Those are sequential. We can use the positions to get things out of them, but the associative stuff like sets and maps, we are not able to count through them in the same way. And then things like stack queue and priority queue are just different animals altogether. For those of you who took algorithms, you kind of know what those things are. For those of you who are going to take algorithms in the fall, you'll find out a lot more about those very soon. But these were our sequential ones. We've kind of seen them. We did blackjack with this stuff. Some of them only support iterators. Some of them only support iterators in one direction. There's lots of performance optimizations and benefits that we get out of these. So if we think about associative things, it's really just sort of a matrix of sort of keys or key value pairs, and whether or not we have duplicate keys or duplicate keys in our key value pairs. And then whether they're sorted or unsorted. So you can kind of choose your flavor there depending on what your problem is you're trying to solve. But all of us should realize that all of these things are optimized for speed, where we don't go searching for something with a loop. We give it the key and it gives us the answer. Okay. So that's a real advantage of these associative containers. So if you take algorithms, you'll learn that. If you've already taken algorithms, you should already know that. And then prioritized queues and stacks are in this family as well. So that's just kind of a lot more than any one of us can fit in our brains, like all of the details about that. So we should be able to look them up and understand that we can use iterators to travel across all containers, which is really nice. Iterators allow us to just have an indirect way of checking each thing. Not that we can go to position 12, but we can go to the next thing and the next thing and the next thing. And one of the key data structures that we need is this pair class. This is for key value pairs. It also gets used for a variety of other things in C++, but it's a tuple of sorts, for those of you who know Python, a combining of two things together. And we use templates to define that. So when we pull something out of a pair, we don't have methods to do it. It's really just a simple struct or data structure. So we pull out dot first and dot second if pair is actually a full instance of that thing. So we use that in our Facebook homework assignment to pull out the key and the value of a particular map where we were looking at people or friends and things like that. Okay. So those are kind of everywhere. And so they kind of work their way into our code. And they're just a little different than some of the other C++ standard classes because they're not methods. They're actually letting us get directly at the data members. So when we think about a container like a map, it's just boxes with pairs. And each of those boxes has this sort of indirect idea of accessing it via an iterator. So iterators, we've said, they come up in all kinds of languages. An iterator is just an abstract concept of starting at the beginning and getting the next thing and the next thing and the next thing until we hit a bumper at the end. So obviously the bumper isn't anything we can make use of. It just lets us know that we've kind of fallen off the end of that little train there. Okay, so they're kind of like pointers. But now that we've learned about overloading of classes, we can probably realize or understand that probably what we're experiencing with these iterators is an overloading of the iterator class to make it act like a pointer. And that gives us a really familiar pattern that we can use using our dereference and our arrows and all that good stuff. Okay. So I won't dig into that too much, but basically when we create a map, we give it the key value pair. And now we have to add things to it. So it's an empty map, or think of it as a dictionary. And we could insert a pair, or we could insert a pair that way. So how does C++ know that those curly braces should turn itself into a pair? It looks at the insert method and figures out, oh, you're looking for a pair. I think I know how to turn that into a pair. So it doesn't magically do it. It has to be able to detect the data type, which often happens when we use those curly braces in C++. Now, the other thing we got to watch out for with the maps we've said is square bracket access is pretty cool, but sometimes using it in C++ creates the key value pair when all we were trying to do was see if there was one. So that piece of code right there will create a key value pair for Apple if one didn't already exist, which causes lots and lots of bugs. Okay. So we can initialize them this way, of course. So there's our kind of mini dictionary of a histogram or, quantity of inventory, however you want to look at that. And we use that for a variety of things. Very powerful. It's the one piece of C++ you should know how to use if you're going to go on and solve real world problems, because it's really, really optimized and very handy. Quick things about const real quick. Const is another thing you will run into the more coding you do in advanced C++. It seems really simple, right? It's like, hey, I can't change A, or I can't change this pointer to something else. But it kind of gets more complicated when we start putting it inside of functions and using it in different ways. Here, we're just saying, hey, you can't change that, right? You can't change what's at that location. So the data at that value can't be changed. And because it's not a reference, we can't even modify it so that the pointer is changed in any way. Okay. So here the value cannot be changed either, right? So this is not a pointer. It's just saying it's a reference, but it can't be changed. Seems like contradictory, but that's a fast way of passing a reference without using a lot of memory to pass that thing. It's like, hey, here's a reference to this, and you can't change it. So we tend to see that a lot in C++. Okay. Here's a constructor or a data member that can't be changed, etc. Okay. So const, the location of the const changes a lot of things. When I move it to the other side of the return value, it says, hey, this method itself is not allowed to change anything. Okay. Putting it over here doesn't really do anything for us, right? Const void or void const is really not a thing, right? So this is really what we got to do with const if we want that method to be locked down. Okay. And we can't have const functions. We can only have const methods. So useful to remember that. Now, two ways to access a string. Of course, we can create an array like that. We can create a const character string. So we're really pointing to, this is a pointer to the first character, and it's going to end with a \0, which most of us don't realize is tucked in there. That's how we know when we get to the end of one of these special constant strings. We can't change it because it's constant data, so we can never change those things. Okay. Typically, we see stuff like this, constant data members, which we can change. We can initialize them through the constructor initializer list. This will come up on your final exam essay question. So if you have to change a constant data member in a class, the only way you can initialize it is through the constructor initializer list. So we can't come back later and do it inside of the body of our foo. That's not going to really work because we've already created val and now it's locked in. So the constructor initializer list gets around that problem. So you want to remember that. Okay. Constant member functions, we said that can make it not able to change anything as opposed to this stuff which doesn't do anything for us. That's just a void method. Okay. So there's nothing really useful in putting that there. And we can even have these const classes, but when we do it when we create them in main. Notice I'm putting the const over here that says nobody's allowed to change that thing. It's really like const int x. So we're just saying, hey, x can't be changed, or foo2 can't be changed. Okay. So that's okay, F1, but definitely not that. Okay. So useful to know about if you want to dig into some of the practice problems. There's a link for you there. If you want to go over some practice questions, that might give you a little extra kind of perspective on it. The only other thing on const is that if we want to lock things down really hard, we use const expr, and that says, hey, the compiler has to be able to figure it out without any user input. So we can do that, but we can't do that, right? Const expr means, hey, I can't wait around for this user input thing. I need to know at compile time. So that would cause a fail for us. And that just gives us an extra amount of control over whether or not something can be changed. Okay. Yes, question.
If user input was of the was const txtr double user input, wouldn't work, right?
No, yeah, because we still can't force a value into that location, unfortunately. Yeah. Yep. Good thought though. So that's const expr. The other thing that went along with this, and we didn't do a lot with mutable, but it is really useful because sometimes you just need a little scratch pad piece of information inside of a class where the class might be totally locked down, but you just need a little corner space where you can take some notes, right? So mutable are typically used for data members in a class where you just need to keep count of something. You don't want anything else to change, but you just need a little escape door where you can do a little bit of calculation. So the mutable allows us to do that. Even when the environment says, hey, you can't change anything like in a constant method or a constant class. So we can get away with that because that's just what mutables allow us to do. They allow us to mutate stuff. Okay. So you may run into some of that stuff from time to time. And a lot of times people put M underscore in front of that just to remind yourself that they are, in fact, a changeable data member of the class. Okay. Little practice problems on that one. Static. I love static. It's important because it kind of brings into focus what happens with our classes. So if our classes are factories, they create instances, but sometimes we want to leave some data members at the factory itself. So we can set these values inside of a function. Oh, so let's talk about functions first. So a regular function, of course, this gets created and then it goes away. So even though I increment it to a 1, it's going to get reinitialized every time. So, but there is a sneaky way to make your functions act a little bit like a class. I can say, hey, this is not going to go away. Once I initialize it, I can increment it over and over and over again from inside of this function and nobody else can see it. So it's like a little secret thing that's locked inside of your function that has some memory, which is kind of a weird thing, but it actually comes in handy in a lot of situations. You'd be surprised. So if this function wants to know how many times it's called, it can actually keep track of that. And nobody else can kind of see that. So there's some fun things you can do with that inside of your function. But where we really use it is kind of in classes. And as we've seen, and you'll see it on the final exam in your essay question, if you want to count how many widgets are created at the factory, just keep count every time your constructor is called. And then you can also use that maybe as a unique identifier. Like this is widget 1, this is widget 2, this is widget 3. We could actually store that inside of maybe the widget's data members, right? That go inside of the widget class. Okay. So count is just staying at the factory. The widget can have any data members it actually wants. Okay. The other tricky thing about using statics in classes is we have to initialize them outside of class. This is another one that's going to be on the essay for the final exam. You're going to need to initialize your static data members of your class outside of the class. And notice that there's no static down here, right? It's just int widget :count, okay? So we're initializing that thing at the factory. And if we wanted to increment it outside of it, we could, right? We just say, go to the factory, increment that particular variable, assuming it's public, right? We could actually do that, okay? But you're gonna need to do this for main and kind of understand this, or for the essay and understand that strategy for the final exam. That'll help you on that one. Okay. And you'll see that in the practice problem as well. Okay. We can create static methods. And so the idea of a static method is kind of like a getter for a data member at the factory. So we can have our factory have lots of methods as well. Those are separate from methods that we might have inside of our widget. Okay. So you just got to think about what kinds of methods you want to have that are generic, that are associated with widgets, and you just want to call them directly from the factory. So a lot of times you might have some static methods in a math class. It's like, hey, I'll just call the math class and use the square root thing or whatever, right? So you can design stuff that way if you like. Now we can use the instances of a widget to get access to, sort of we like travel through the instance to get to the count, but it's kind of a weird thing to do. It makes it look like, sorry, not the ID. This one is the one that's traveling through the class and getting to the count, okay? The ID is not static. Let me get rid of all my scribbles here. The ID is not static, so it lives inside of each instance of the widget, right? The static one over here is the one that actually only ever lives inside of the factory itself, okay? So typically, we would actually access that thing using widget double colon ID, or widget double colon count, or widget double colon print count, okay? Those are our static methods and static IDs. There we go. There it is, widget double colon print, okay? And the weirdest one is static const int. We can create a const at the factory, so to speak, and then initialize it to something like pi. So we could have a math class that has all of the important math constants that we never want to ever change. We just make them static const and put them directly inside of there. And you can initialize them directly inside of the class or down here, but not both, okay? So you can initialize outside or inside if it's a static const, okay? Practice problems there if you want to go over that, okay? And on the static, mutable, and const over there as well. Okay, so high level memory layout is just sort of our zeros and ones. They call it text, but it's really the executable code that got compiled into zeros and ones. So it's all of your good code that you've been writing all semester. When you have a variable, we've always said it comes and goes inside of scope, right? Terrible curly braces. So that's really a stack, just like a pancake stack. If you go into a function, all of the variables in that function become variables on the top of the stack. But when you leave the function, they get popped off of the stack automatically. That's why we tend to call this automatic memory, as opposed to when we ourselves put on our construction hat and start building cool data structures on the playground, the heap. Anytime we create something new, we get a pointer and we start hooking pointers up like Jigsaw Puzzle and Facebook, and we start building these exotic data structures. And that's what most developers end up doing, is building lots of really exotic data structures, okay? And we got to delete stuff that's in that memory. Otherwise, we fill up memory and a program crashes or gets really slow, or computer gets slow, etc. Okay. And then there's some special areas. We won't dwell on these too much, but that's pretty much how C++ lays out its memory. So this is the game plan for C++ while a program is running in memory. Python and Java do it differently. This is how C++ does it, okay? So just reminding you that when we have a for loop with a variable, that variable is going to get created and then go away every loop iteration. So it's kind of crazy, but that thing is going to sort of come and go 1,000 times when you run that for loop. It gets created, we do something with it, and it goes away. The I is special. The I stays around, but this one goes away every time we do another loop, okay? Which sometimes we forget, okay? It's really part of this scope, okay? So it can go away and it can cause us to have some problems, okay? One of the problems that we could have is this one. If I create a new piece of memory and I'm looping around, I'm kind of resetting it every time, but I'm never deleting the character. So this comes and goes every time, but this sticks around. And so this was our classic memory leak. Every time we loop around, we leak a little bit more memory. We got to delete that thing in the context of the loop. Otherwise, we lose the pointer to it, unless we have some other way of remembering that pointer. Okay. Because that pointer is going to go away now, right? Fully. And we can't really delete that stuff. Okay. So that's our classic memory leak. Okay. So the four models we looked at was like, hey, let's create a dynamic array of integers. So that's probably the most common thing you'll do with C++. If you don't know how many integers you need, you'll say my array, which is a pointer. What kind of pointer? Pointer to an integer, right? Points to an integer. Always it points to the first thing in the array. And here's me creating 4 of those, right? Size of those, okay? So now I can delete the array and everybody's happy. Probably we should set that thing to null right there. Sorry about all my messy colors over here. Come back and fix that. So we should set that to null. And we got to remember to do this, not this. For every new with square brackets, there must be a corresponding delete, not that one. Okay. So that's kind of our first approach to doing this, right? Now, here's a couple things you might not have seen on one page with the arrays, or probably saw it in lecture, but here's the typical stuff we might do to initialize our arrays. And we can leave out the equals here if we want. And here's us doing that dynamically, okay? And we can't use the equal sign here, which is strange. And we can initialize to 0. This is really helpful because most of us forget to initialize these things to 0. And now we just have garbage. But this is a little secret way of initializing to 0. And here's us assigning hello world. And we can't use range-based for loops with dynamic arrays. If you used new, unfortunately, there's no way to use our range-based for loop. Those are only reserved for these up here. Okay. Small facts. Okay. Now, next level was creating an array of pointers. What do we mean by an array of pointers? Well, if this thing is pointing to the first item in the array, the first item is going to be a pointer. So my array is a pointer to a pointer. What kind of pointer? Well, it's going to point to an integer. So it's an integer pointer. So this points to a pointer, which is going to point to an integer. Oops, wrong one over here. That's the one I set up. Okay. So this is where our double pointers come from. So this is also important for your final exam essay. If you have to create an array of pointers that, let's say, point to rows of other pointers, that's a two-dimensional array, right? So these are pointers that point to individual things that are in each of the rows, right? Kind of like building our triangular array. So if you all remember, creating the triangular array was somewhat similar to this, okay? So this is probably the area that will give people the most indigestion, right? Is that you're going to create some two-dimensional arrays of something, probably two-dimensional arrays of pointers. So we're going to be in the double and maybe triple pointer scenario, okay? So you might want to just review some of that. I'll give you some links here in a second, okay? But the moral of the story is, delete in reverse. So delete the ornaments on the tree before you delete the tree branch. Think of it that way, right? So I have to loop through that thing and find the non-null pointers and get rid of those. And then we can go ahead and delete the whole array like that, okay? And I know you guys did this with your triangular array lab, so it should be somewhat familiar. So the rest of it is just changing the data type. So instead of an integer, let's just switch it to numbers. So this is an array of copies of an instance of a class called num. So we have to call the default constructor there in order to build that array, Okay. So if I go to position 0, I can pull out anything I want by using the dot operator. Okay. So I could say my array square bracket 0 dot data member, because the actual instance is in there. In this case, it's not a pointer that we're storing the actual instance. Okay. So it's trivial to just get rid of the whole thing. That would trigger the destructors for all of our num instances, just so you know. Okay. And we wouldn't do it that way, right? Because if we create it with the square brackets, we delete it with square brackets. Okay. And then the final one, I'll kind of breeze over this because it's really similar to what we saw before, but this is us creating an instance of the number class with a 12 and getting a pointer and storing the pointer over here. New always gives us a pointer. So this has to be a pointer. A pointer to what? A pointer to an integer or to a number, right? So that's how we get our pointer all the time from our new, okay? Okay. Uh, so similar to doing it with actual integers, we just switched our data type to num in this case. Okay. And then we'll delete that whole thing. So there's some practice stuff there. These are kind of tedious, but really powerful if you want to actually, get used to that syntax again. Okay. Let's talk about class destructors briefly. When we delete a class or when the class goes away, we will trigger the destructor. So here we're saying, hey, follow the pointer. So this is a pointer here, right? This is a pointer to an instance. So when we delete, I'm not deleting foo, or I'm not deleting f pointer, I'm deleting what it points to. So this is what gets deleted because we're following the pointer to what we want to delete. That confused me for a long time when I was first starting out. I'm like, I thought I deleted that thing, right? So I'm just deleting what it points to, okay? So that's what triggers our goodbye message from our destructor, because we are actively deleting or cleaning up our mess, okay? Now, we talked about conversion operators. They're a little bit strange, but they are one of the masquerading tricks that classes can use to make us think that the class is something else. So if I have a single argument constructor like a number class where it just needs a value, I can do something like this. It's kind of crazy. N equals 1 or 10 or n equals 5.5. So C++ goes, that's an instance of a class. This is an integer. How am I going to solve this problem? Oh, I know. I'll just put it in the constructor and build a new one. So C++ is going to turn that into an instance of a class and copy it over the N. Okay. So that is automatic conversion. But we can turn that off by putting the word explicit in front of there. Okay. So that prevents that behavior. It's like a safety valve we put in the class so that people don't accidentally write code they didn't know what it was actually doing. So when we're the designers of the class, we can decide to be more stringent about that if we want. Okay. Conversion operators are like an imaginary number. We have a real and imaginary part. If someone says, hey, I just want you to print out F. Well, what is F? It's an entire instance of a class. So what does it mean to try to print it out? So cout says, hey, can you give me something I can print? I can print a double. And that's where the class comes in handy and says, oh, I can do that. I'll convert myself into a double and you can just print that. So conversion operators don't have return values here, right? It's a method for a double, and it doesn't have a return method because we know what it's going to return. It's going to return a double, okay? So you can add multiple conversion operators to your class, although it can cause your class to become a little bit fluky if you have too many of them. So kind of got to be careful from a design standpoint when you start throwing a lot of those in there. but they are a really handy way to make your class printable if that's really what you want to do. Okay. So that is called a conversion operator. And then the big one, the copy constructor. So we learned a lot about this when we were getting to know smart pointers. So copy constructors happen when you are constructing an instance. Okay. So if you ask yourself, am I creating an instance with the following code? If the answer is yes, then you're probably using a copy constructor. So by default, if you have a class, the copy constructor is kind of like this. And I just sort of put some, documentation in there so we can see it, come to life. But it's secretly in there. It's invisible unless we add one. So if I say F2 equals F1, I am constructing F2 based on F1. And that is the definition of a copy constructor. Okay. So if I were to do that, it would trigger any code that was inside of this specific definition. This specific definition isn't copying anything, unfortunately, it's just printing a message, but we would, in real life, add some useful code to that. This is different. So let's take a look at this. Am I creating something here? No, F2 exists, F1 already exists. So this is not calling the copy constructor. And I know it's confusing, but this is where construction happens. That's going to trigger this thing here. We'll see the assignment operator here in just a second. Okay. And then, of course, our class goes away in scope and triggers our destructor. Okay. So this is assignment, right? So we'll see that differently here in a second. They're very closely related because, there's multiple ways that we might steal some copy of something to use in some other variable. Okay. So here is a properly implemented shallow copy. Hey, I'll take your value, copy it into my value. Notice I threw this in here. This is optional. We could leave it out if we wanted to, but it just makes it more clear. It's like me, my value versus your value. Okay. So that is a very simple copy constructor. And so now we get the message and we get the value copied over. Okay. Which sometimes can be a good thing, sometimes not. Now, just pointing out that the same thing can be done with const ampersand. Why would we do this? Well, foo doesn't take up small amount of memory. This is a foo class. So using const ampersand says, let's do it fast, but let's do it safely. You're not allowed to change this one. You can change yourself, but if we try to change this one, we would get a compiler error. So this is why we see this so often together. Const, data type, ampersand. It's fast and secure. In other words, we can't mess around with the thing that was given to us and change something else outside of the scope of our constructor. Okay. So that is something we see in various places. So here comes the assignment operator, the close cousin of the copy constructor. So here's the situation. I have two things that already exist. And I decide that I want to copy this one on top of this one. So by default, this is not calling the copy constructor, but the default assignment operator. And it is really just going to copy over the value from here into here on a per attribute level or per data member level. And that's not always a good thing because now we have this abandoned thing over here that's a memory leak. Okay. And so it can cause problems. This is what we call a shallow copy. And it's what C++ does by default. If you try to say, hey, I'm just going to be a copy of you. And now you are sharing a pointer, and this leads to a lot of bugs, a lot of bugs if you have pointers in there. Okay. So we need something that does the right thing. And again, we used our triangle matrix lab to sort of do this. So there's I'm returning an instance of a class. right? And that's so I can use this in a chain of operations. But essentially what I'm doing is I'm changing my value to be your value. And then I'm returning a instance of myself so somebody else can use me in an equation. Okay. So if you say A equals B equals C, that situation would work, right? And that's why we have something returned. So you can chain these things together. But most of the work is done right here. I've updated myself and I'm mostly done with the operation. This is just so I can be part of a larger equation, which is a little bit advanced, but still pretty critical to do. Okay. So that is my assignment operator. Okay. So now I can say F2 equals F1, and I will have copied things. It's still a shallow copy, but actually, we at least can see how things work on the inside. If I don't want that default behavior to happen, all we got to do is use the keyword equals delete inside of our class. Delete the copy, delete the assignment. This prevents our class. It's kind of like that const exp. It kind of ensures that none of this fancy extra behavior actually happens inside of our classes. Okay. A lot of people don't even know you can do that. They just sort of let it go. But as we saw with our unique pointer and our unique pointer, we had those deleted. We could not copy or assign unique pointers anywhere because that's not how they're supposed to behave. So sometimes those things are an important part of the class. Okay. So that's our copy constructor, destructors, etc. So that set us up for the conversation about shallow versus deep. If you go anywhere and you code in C++ and someone says, hey, make a copy of this, like that's like someone handing you a really sharp knife. It's like, okay, I really got to study my data structure and see what it means to make a copy and how are these copy and assignment operators going to affect me while I'm doing that. Okay. So usually, if I'm going to do it the right way, I got to implement my own and probably a destructor as well. So that tends to be called the rule of three idiom, which is kind of a really pretty wild thing. But basically, if you kind of do this and this in a really fancy destructor, like we did again on our triangle matrix, that's typically how you have to solve these problems. You kind of got to do all of them at once and do them very, very well. Okay. And so we did that on that particular lab. Okay. So, but if we didn't do that and we think about our jigsaw homework assignment, we'd kind of have a mess, right? We'd have two puzzles that may be trying to delete or change the same data structure, and we could have a lot of problems with that. So that's kind of very shallow and generally probably not a good idea. There could be a useful reason for having one set of puzzle pieces and two different ways of arranging them. So that could be a useful data structure. That's a less shallow copy. There's the common stuff in the middle. Whoops. But if we truly, truly, truly want to make a copy again, which we try to do in our triangle lab, or triangle matrix lab, that's kind of the stuff that we were doing. I think most of you guys kind of managed to do that okay. Okay. A lot of pointer stuff in there, a lot of news, a lot of deletes. But if you can do that stuff, you're really, doing some advanced stuff. Now, because pointers cause so many crashes, we invented or they invented the smart pointers in the memory library. And we'll just kind of breeze over this. I know everybody kind of probably got enough of this with the Facebook stuff. But unique pointers are kind of limited use. You can only point to one thing ever, and no one can ever take that away from you. So you keep your program pretty stable. But there's often a lot of times where you need to point at the same piece of data by more than one pointer. So those things wouldn't be good for that situation. Shared pointers do that for us. And shared pointers really act the way languages like Python and Java act. They're basically saying, hey, when the last person leaves the room, I'll turn out the lights. I'll call the destructor for the little piece of memory that I am managing. So it's one type of garbage collection similar to what happens in languages like Python, where nobody else is using a particular instance of a class anymore, and the garbage collector just comes around and cleans that up. It's a little different in Python than this, but this is the same idea. It's like we don't want to have to, as coders, worry about calling the destructor all the time. So we'll just use one of these fancy pointers. And as we saw on Facebook, the weak pointer is just a way of monitoring a situation without getting involved. The weak pointer doesn't affect the, the, the elimination or destruction of a particular piece of memory. It just lets us check in on it in the same way we were checking to see, hey, I had a friend in my friends list in Facebook, but it looks like they removed themselves from the platform. Okay, so now my weak pointer isn't valid anymore. So most of us kind of ran into that at some point. Okay, so those all came from the memory library, and those were templated classes. So I won't dig too much into this, but when we use a templated class, what we're really saying is the unique pointer class will create an instance of foo for us. So we need to sort of, or it'll manage the pointer to that. And so we need to give it a pointer to start with, right? So we call the foo, we create the memory, and then the pointer gets passed in and managed by this instance of the class. And we see that thing kind of a lot. We saw it with threads. We have a template for a type. We give it some information, and it kind of takes it from there, and we don't have to really worry about it after that point. Okay. So, but we are kind of feeding it a pointer and telling it foo, not foo star over there. Okay. So it's just foo as the data type. Okay. So typical things we might do, right? We can sort of check to see whether the instance of the class is the same. These are two different instances of a class, so they are not going to be the same instance. They have different sort of places in memory, right? And it turns out, of course, that they are also, in this case, managing different little pieces of memory on the heap, right? So that's this and this, the 1 and the 2, okay? So of course their address is not going to be the same thing. So if I say star IPTR, I'm just overloading or using the overloaded star operator to get at that piece of memory underneath that's being managed. Okay. And this would trigger our compiler error because we can't actually do any kind of assignment of those things. That's been taken away. Okay. So that was our unique pointer. Shared pointer is pretty similar. Just a quick review on that here real quick. Oh, and we said we can create vectors of these. So that's pretty amazing. We can stack up these different kinds of things, and they're all able, if we can sort of see our way through all of the syntax, we're now really using code in the best way possible. We have these things that are self-contained. We can put them inside of another data structure that's self-contained, and they trigger each other's destructors. The vector destructor triggers the destructor of the unique pointer, which triggers the potentially destructor of some pointer that it's managing. Okay. And then we have our iterators again that we can just go across all that for. Okay. So pretty cool. Once you understand the individual components, you can start to assemble them in very, very powerful ways. Okay. And there's our iterators again, looping across those things. Okay. So dereferencing an iterator gives me the pair, right? And so in this case, we need to, or it gives me what it's pointing to, in this case, a unique pointer. And so then dereferencing that gives me actually the thing that it's pointing to. So it is a little tricky sometimes working with iterators and then unique pointers inside of those. So just a little tricky bit for you there to kind of think through, but pretty elegant in code. Okay, and there's some quiz questions there for you on Quizlet. So shared pointer, really similar. I'll go over quickly. I know we're just kind of keeping track of references. So as I add more pointers to the same memory, they all have the same use count increase. So they're using static data members at the shared pointer factory to keep track of how many things are being managing a particular piece of memory. So lots of fancy stuff going on in the background using probably static data members in the class. So but we get the benefit of it just sort of knowing how many things are there. And when everybody's gone, the last one triggers the destructor or deletes the memory. Okay. So there's our shared pointers. And for those of you who are doing any threading after this, heads up, because they're not super thread safe. So you might run into some troubles there. So we can use them with classes. So we saw with integers or with classes, but we still got to create somehow a pointer to that class and pass in all of the constructor arguments needed by that class. So we need a name of our tool or whatever else kind of goes along with that. Okay. And then we can just treat it like a pointer. Jeff, arrow, tname, right? That's an overloaded arrow that is interpreted as taking me into this particular instance of the class so I can grab its tname. Okay. Okay. And all of the other stuff works the same as it would with a data type like int, basically. Okay. And there's our shared pointer review. Now, the last thing on this subject, I think, maybe a brief slide on weak pointers, but make shared, if you recall, is a safer way. Instead of doing this, right, instead of us creating an instance of something and getting a pointer, we can just say, hey, you do it, right? I'm going to give you the constructor arguments for you to create a string, okay? So make shared actually says, I will go create an instance of string with those arguments, and I will give you back a shared pointer, okay? So that is a little safer because that way nobody can muck around with that pointer up top, right? So all of the construction happens in a locked box versus up top where somebody could be like, hey, I'm just going to give you a pointer to something, and then later on, I'm going to destroy that pointer myself, right? So that could really cause us some problems. So we tend to not want to do it this way, okay? So that's why we kind of introduced the make share, okay? And the weak pointer we said is just for monitoring. So I won't kind of dig into this too much, but we can use it as we did in Facebook to find out how many shared pointers are currently managing a particular chunk of memory. Okay. So here we can use our weak pointer just to watch that situation. Okay. And here's just some code. And some of us, most of us eventually figured out the expired thing for our friend pointer in Facebook. That was the key thing, or some kind of validity check before we tried to follow that weak pointer so we didn't get a crash. Okay. So you may recall some of this stuff from the Facebook homework. Okay. So let's see. Think these are just, yeah. So this is really probably something that everybody already has in their minds. We're just using it to keep track of references to items in a vector, or maybe number of times a particular class has been instanced. Okay. And some questions there you can go over. So that's our end part one. Take a breath. So part two is smaller because I've carved out a bunch of stuff, but part two is going to cover this stuff. So now some of this stuff is not going to be on the final exam. So exceptions are not going to be on the final exam. Threads and mutex are not going to be on the final exam. So you don't have to worry about these parts. Okay. And I know we did some of this stuff more recently, so you might be feeling up to speed on this, but this is what I'm going to cover next. So I'll give everybody a chance to decide if you want to hang for that. But I'm going to try to get us through that by 7, I think maybe a little after 7. So just forewarned if you feel like you got to get out of here. But let me kind of dive in then. Threads. Actually, there might be a little bit on threads. So I'll check and you'll see this on the practice problem. I thought I pulled them out, but here they are. So just in case, remember that our main program is a thread. And so if we don't spawn any new threads, we have one thread always. But here we're going to spawn some threads and then rejoin. And so they go off and do some work. And we wait in the same way that we wait for a CN. We wait here and we don't move forward until the thread is done with whatever it's doing, which could take a split second, or it could take 10 minutes, or it could be never, in which case our program is locked. We call that thread lock. But all normal termination eventually ends up finishing the program. So for homework 8 and for our restaurant, if your program terminates, then you've done everything you need to do. If it doesn't, then maybe there's some problems there. So that's kind of important thing to keep in mind. The other idea is that threads need a function. So it's not like they necessarily need a class. They at minimum need a worker function that can just act like their own personal main. So when I launch a thread with a worker function, that worker function becomes like its own personal main for that particular thread. And we can launch that same function in multiple different threads, right? So I can have thread 1, thread 2, feed it different arguments that will be passed into that by the thread constructor when it launches that particular function, okay? So we're probably all seeing that for folks who are thinking about doing homework 8 at this point, okay? So there's our typical structure for rejoining our threads, okay? So threads are just an instance of a class like everything else we've created, or many things that we've created. And so the constructor is really all we need to call, and it will launch our worker function for us, okay? And there are very few things that we can do with that instance once we do it. Basically rejoin, detach, ask a few questions, or maybe assign this to something else, okay? So the main thing we need to remember is these are the arguments that will be called by this. So if you remember our discussion about pointer variables, and we'll see that here in a second, this particular constructor's first argument is a function pointer, okay? Function pointer to a function that can handle some arguments, right? Depending on the kind of function that we pass in there, okay? So here's a question. Given the following function, does this code compile and terminate normally? We launch a function with B and with B, and the thread function that we're launching is just going to check to see if what's at B is equal to the opposite of what's at B, okay? So we'll compile, we get a runtime error because we need to rejoin both threads, right? We did not actually rejoin our other thread there. So that's going to cause us a problem, okay? So just keep that in mind. Thread question 2, we're going to add, does this one compile? So we have T1, T2, these are both joined, should be just fine. Yep. You can't really tell what the output's going to be there, but that's all right. Mutex. So our mutex is a way of signaling that we're actually not available. The memory is maybe currently in use, right? So we looked at using a mutex as a way of synchronizing our threads or stopping one thread and having it wait while we're busy storing some information, okay? So there's our address to our mutex here that we can lock or unlock inside, okay? So inside of our worker function, we would lock. And if we don't get the thread lock, we all wait right here, right? Anybody who isn't lucky enough to get that, only one thread can get it, has to wait, like we're waiting on a CN. And then otherwise, we get to go to work, selling inventory, etc. Okay. And eventually we have to unlock before we return, right? So this is a little bit of hidden over here, but we have to unlock before we actually return from the function or move on to the next loop in this particular case, okay? So if we get stuck, essentially what happens is one thread is here waiting and the other thread maybe finishes because it forgot to unlock. We are stuck in a thread number 2 and never get to get out of that situation. And that's our thread lock. Okay. So some of us could end up with that problem in the homework gate restaurant situation. Okay, so you got to just kind of make sure you structure that properly. Okay, so in this particular case, here's a thread function. We kind of lock it, we increment a value, and that's all we do, right? So that's going to be deadlocked because obviously we did not remember to unlock that mutex. So we have to remember to do that, obviously. Okay. See how I'm doing on time here. Here's another one. We lock, we increment, and we unlock. This one's okay, right? So this particular situation is fine. And we'll get, if we trace this through and we pass in value 0, right? This one's going to increment it. This one's going to increment it. And this one's going to increment it. We'll get a 3 after all of that. Okay. And I'm going to skip over these here. I'll let you guys come back to these just because I think we're going to probably be a little scrunched for time. So I do want to talk about inheritance because that is going to be important for your essay question. So remember that when we inherit from something, we got to have this public up there right next to the class. That tells us that we have access to everything that is inside of the FOO senior class, if you will. And if anybody derives from us, then they can have access to that stuff too. Okay. So we inherit the data member or attribute of the parent class. And so we can access it as if it came from FOO Junior. Okay. So I think we all saw that a bunch of times. Okay. And hopefully everybody remembers chess. So here's an example. We have a base class, and then we have class A, right? So class A has a class called base, okay? So base is a class inside of A, and then B derives from that class base, okay? So which class derives from the base, A or B? Well, hopefully we know that this is derivation, and this is what we call composition. This has A has a data member that is a different class. This is the actual class that's doing the deriving, okay? So maybe super obvious, but just wanted to put those up on the same slide together. So this we've called composition in the past. Been a while, so you might forget about that since the last time we talked about that. Okay. The other key thing about derivation is we have to have a default constructor in our base class. Notice this is not a default constructor. So if I try to have a derived class, we're going to have a compilation problem because it's going to try to create the base class and then do this, but it doesn't have the information it needs to create the base class. So what we have to do, is we have to add the default argument for our base class, and then we can come back and modify that if we want. But it's always going to call the constructor silently for this if we don't do it ourselves. Okay. So here's another example, base class, default constructor, which is good. And so here, even though X isn't really getting used, it's going to call the base class and it's going to set this X equal to 5 all the time. Okay. Which isn't particularly useful, but it's good to trace through these things and understand how the mechanics work. Okay. So here's us with base class with no constructor, but it really is a default constructor because that's the way classes work. If you don't give them a constructor, they get one. So this one would work okay. Okay. We still haven't really done anything useful with this thing right here. We've just sort of ignored it and haven't done anything with it, but we could if we wanted to. Okay. Even simpler, totally works. So when you're creating your essay problem and you read, oh, this needs to be the base class and this needs to be the derived class, start like that. Don't let it throw you. Just write that down first because that works. And then you can say, okay, what data members do I need in my base class? What data members do I need in my derived class? They're not going to be that complicated. So then you see a lot of, things that you got to do, just sort of whittle it down and get something compiling. If you write a lot of code and it doesn't compile, it's not going to help you too much. So just get that in there and get it compiling and you'll, at least have a solid base to build on top of. Okay. So when we need to initialize our data members, just reminding you, so in foo here, I can use my constructor initializer list, right? To initialize, I can say, take this value and copy it into there. So that's just a normal constructor initializer list. In the derived class, if somebody gives me FV, I could do it this way, and that'll work, but it's going to be after it constructs this using the default, and then it overwrites that value, which is okay, but not the greatest way to actually do it, okay? So it's better to do that by calling the constructor for the base class in the constructor initializer list, okay? So, but let's take a look at this case here. So X is going to get 5 all the time when we default construct the base. It's kind of silly, but that's what this example is doing. So if I have X here, it's going to call the base constructor, then overwrite the 5 with whatever somebody gave me, okay? So it will work. It just seems like a little bit of a silly piece of code, okay? In the cases where we fail to do that, right? We cannot, well, one thing we can't do is we can't try to initialize this directly. That is not going to work. X is not part of this class, so I can't do it here. I have to call the base class constructor directly in the constructor initializer list. So let's go take a look at how we do that, okay? So this is, so this one will fail, right? This one cannot be initialized on that line, okay? What we need to do is, instead of doing this, let's get over to the situation that does work. This is what we really want to do. Foo 10, like we all saw with the queen, and also all the other pieces, we're going to call our base class constructor, give them the arguments they want, and then modify ourselves whatever we want to modify about our own data members in our class, in the derived class. So we're on the constructor initializer list, calling the constructor, and then doing whatever we want. And I think there's a comma in here that's being hidden by this thing right here. We should be able to see a comma there. Okay, so now we can actually do that kind of construction. Okay, last question on these things. So here, let's see, does the derived class compile? So const x, right here, we're sending this underscore x into the base constructor, but this one doesn't take any arguments. So that's going to fail, right? So that is not a matching constructor, basically, okay? Now we're okay. And this, again, you're going to want to know this for your essay question. If you have a const in your base class, the only way to initialize it is like this, okay? So if you try to initialize it in here, it's going to fail because we've already locked in the 0 value. So if you want to initialize it, you've got to do it through your base class initializer, okay, or your base class constructor, okay? Okay, inheritance access. I'm going to try to go lightly here. If something is protected in the base class, it's kind of like all in the family, but nobody else. That means the Foo Junior can use it and give it away, but nobody else can reach into the class publicly and grab it. So we can't say, JFR.x, but we can say, just call the constructor and see it, or maybe have a public method down here that releases it into the public in the junior class. So protected just means nobody can grab this from the outside world, okay? But the junior class can expose it if we want to, okay? So here we have protected data members and a protected constructor, okay? So I can call this and give it this, but I cannot access X, which is okay. Maybe that's not really what we intended it to do. Okay? And then here we have protected const int, passing it through the constructor. We're going to try to initialize that by passing it. That should work, right? That should not be a problem. Okay, we just can't access the X after we've actually constructed it. Okay, we would need a method to allow us to do that. And here's that method. I can return a protected value from inside the derived class if I want. That's my prerogative. I just can't access it directly via the class name and the dot and the X. Okay, I need to use a public method to get it. Okay. Whew, I know these are tiring. Almost there. So here we have private. So really, this is still going to work, right? I can still do this because the derived class is in the family and it can actually access those things. That's kind of strange. It looks like we shouldn't be able to do that, but we can actually do that. But if anybody derives from us, they will not have access to this stuff that was in the base class, okay? Now, the key in learning all this stuff was trying to set us up for overriding or overshadowing things. So we have a getX in the base class. We have a getX in the derived class. In chess, it was is legal move to. So, and this is a behavior that we want. We want our derived class to be able to say, hey, I got this. I've got a method and I don't want you to execute. So in order to do that, we had to add some special stuff so that we could kind of dynamically control which get X is going to get called here. Okay. So even though we write it, we may actually have some trouble getting access to it through a pointer unless we add that special virtual keyword. Okay. So we can say foo junior get X or foo double colon get X and get a different access to a different method if we want. But if we want to do it through a pointer, we're going to actually have to have some special stuff here. So here was, did I go forward? I think I went backwards. TX to false closer. Oh, sorry. Just inheritance question here. If I have two of the same data member in the base and the derived, it's always going to access the one closest to the child, to the most derived child. So when I say DX, it's going to choose this X by default, not this one. Okay. And it's going to print, let's trace it through. So if I pass in a 20 to here, the 20 goes down to here, right? This actually is going to go here. So that's going to get the 20. This is still going to be a 5 down here. But we're going to see a 20 when we actually run this because we get the X from the most derived child or the most derived class. Okay. Oops, wrong direction. Okay, so that virtual thing. So we said that if we want to collect a bunch of derived creatures in a vector of creature pointers, we can do that. That's pretty cool. Goblin, Balrog, Warp, these are all derived classes from the base class creature. And that, first off, is kind of cool. So I can have a generic pointer from the base class collect instances of derived classes in there. That in and of itself is really nice because I can go through them all and just call a method that they all should have because they derive from the base creature, okay? But by default, we have static binding in C++ unless we put some special keywords in our classes to let C++ know that we want some dynamic behavior here. So we put the virtual keyword in front of the base class in creature, and that allows C++ to save what's called a vtable, so it can decide what kind of move we actually need there. And this is the behavior we have in chess for homework 7. We have a virtual base class is legal move to, and we use pointers to access all of our chess pieces. So when we try to move a derived chess piece like the rook, it's going to dynamically use the rook's is legal move to. Okay. So that was the whole idea for that sort of design approach. But we had to get that virtual inside of that class. Okay. For everything to work properly. Okay. Terminology, pure virtual methods have a equals 0, and that prevents that class from being instanced. So that means we have an abstract class. In other languages, abstract classes are more easy to spot because they use the word abstract. C++ has this somewhat cryptic way of forcing a class to be abstract, okay, as opposed to something is normal or instanceable and something we can put in our game. Okay, so let's see which one of these following base classes cannot be instanced directly. So we have a base class, and then we have a car, and then we have public, right? And then we have, right? And so public, or fruit over here, sorry, public fruit has a virtual method. That's the one, obviously, cannot be instanced, okay? Okay, which of these following base classes do not enable late or dynamic binding? So if this is our base class creature and it has a virtual move, car has something that's not virtual. We have virtual over here, should be the car, right? So if we derive from the car, we cannot dynamically determine via a pointer which start method to use. We learned that we could use the using keyword to sort of re-register something. So we can say, hey, I want this X to be in the public space. So in the public space here, I'm pulling the base class X into the public space using the using. There's no parentheses or anything needed here, no data types. We're just re-registering its access in the derived class, okay? Yeah, and it's still protected over here, so I can't reach in and get it through the base class, but I can get it through the derived class. Multiple inheritance, you won't need this for the essay, but it's good to know that if you want to avoid the diamond problem, where we have student and teacher both with a copy of the person instance in them, so that's the whole instance, we need to inject the word virtual into our derivation clause in our class. So here, student derives virtually, teacher derives virtually, and now we only really have one of these base classes in a copy of that instance, okay? So we can get the behavior we need. So which of these, this is a bit cryptic, I know, but if I have a class X, and then BX derives from X and CX derives from X, and I have DX derives from X, but DX and EX are virtual. Anything that uses the DX and the EX are safe, right? So FDE is okay. GBC is not going to be okay because we're going to end up with two copies of this base class in GBC here, okay? So this is what we need when we're deriving to avoid that problem, okay? Operator overloading. I think I got about 5 more minutes, so hang in there. I'll try to keep it high level. all sorts of things we can do to make a class masquerade as something else. And we saw most of them. We saw we can do mathematical operators. We maybe did some comparison. We may have done one or two of these. We know that our shared pointers or smart pointers use these guys right here. We can overload this. We can make a vector look like an array. We can make an iterator look like a pointer, and we can convert things into different data types. So there's a whole bunch of these things that we can do to change things pretty dramatically. So if we just look in one more time, the name of the method is operator plus or operator minus, and this is what we return. So all we're really doing is adding some code to return a number, an instance of the same class we're currently working in those particular overloads, okay? So the weird thing is we got to think about me versus them, right? I'm adding something to me and returning some new item. The something I'm adding is the thing that gets passed in, okay? So here is our full implementation of the plus, right? Where we're adding something to me. This is the me. That's the thing that gets passed in, right? And then we return a copy of that thing, okay? So that is a copy, right? We're making a copy and returning it, and it matches the data type of our return statement, okay? Okay, plus equals, changing yourself. And so you might think, why do I need to return this if I'm just changing myself? I'm actually just doing that so I can put these in a long chain of equations, x equals y plus equals 1, etc., which is pretty weird, but you can do that, okay? So that's a way of saying make a copy of me, right? Make a copy of me and send it back, okay? Okay, so there's some overload code recognition Quizlets for you. Functors, real quick, they're just instances of a class with one thing overloaded, the parentheses for a function. That allows an instance of a class to act like it's a function. So here we have a functor. That's kind of silly, but basically the value that goes in is the multiplier. It gets stored in the x. So we're putting, let's say, a 1 or a 2 into that x. So here we're putting a 1 into that x. And so if I say f of 2, what I'm really doing is saying, give me back 2 times whatever we put in x over here. So I'm really going to get back a 2 from this one, okay? This one is a bug over here. That one doesn't even really work, okay? So we want to treat f like it's an actual function, not a variable. Okay? So that one won't work for us. Function pointers, you won't need this for the final exam, but remember that these are just variables that hold a pointer to a function. The function returns an integer and has no arguments, or returns an integer and has a where'd it go? Turns an integer and has no arguments, right? So those are all no argument functions, sorry. So these are different variables for holding on to functions that match a particular type, okay? And so we can call a bunch of different functions if we want, okay? Now, if we look at these compared to other variables real quick, pointer to an integer, this is still a pointer to an integer. It's not a function pointer yet. This is a function pointer with no arguments, returns an integer, function pointer that has a string and a double argument. Notice we didn't even need to put the names here. We just need the types, okay? So there's our function pointers, okay? And so we could just do this kind of assignment trivially and then call a function, and that's pretty cool, right? So my func here is really going to be calling the run function, passing in the x, okay? A couple more quiz questions for you. And the last one, or almost the last, was really just syntactic sugar. The compiler lets us do this, It's like, you can use this mini language, but I'm going to use that to write a functor. So these are really just like decorations on top of the functors. So this is what goes into the constructor for the functor. This is what happens when we call the functor as if it's a function, and this is going to be what that functor should return. Okay. So we could pass this into the constructor and then use it later, right? So this has got Q baked in. A Q value of 10 is kind of hidden away inside of that functor right there, so that we're multiplying 10 times whatever comes in the door here, okay? And if we want to change something, we saw this in our lab last week, we can use the reference to actually allow us to make a change. So this lambda can actually literally reach out and modify that if we wanted to, which is pretty powerful, but a little bit dangerous. Okay. Whew, and that's it. So thank you. That was difficult. Hopefully not too painful. So I will get the final exam question out to you ASAP in the morning. I know everybody wants to know. If you have any questions about your grade or want to come by for any review stuff, I will be in my office all day on Monday. Email me if you have questions on your grade or anything at all. Thank you for your attention all semester. You guys have been great. I hope you get some rest this weekend. All right. See you. Have a good weekend. See you on Tuesday or Monday. You come in. So,
How are you?
good.
Um, yes. Yes.
Oh, right. I didn't mail you. Yes, I forgot to mail you. Yeah. So do you remember how we did it for the midterm?
Mhm.
It'll be the same.
Okay.
We did it for you for the midterm, right?
Yeah,
Yeah,
but
okay.
it's gonna be like from Monday to Tuesday,
The-
or it's just that Tuesday.
It'll be, so Tuesday is when the test releases.
Mhm.
So you have all the way until Friday.
Okay. That's
Yeah,
good
so
because
you can-
actually I have a final on
Exactly.
Tuesday too.
Yeah, yeah.
Okay.
That's why I do it that way, because it's more time, but you gotta find a place to do it, right?
Yeah.
And so you can find that time.
Okay,
So,
thank
but
you.
yeah, what you might want to do is email me when you know roughly when you're gonna do it, so I can just pay attention to email if you have any problems or questions. So,
Okay.
okay.
Sounds good. Thank you so
All
much.
right. Okay. All right. Absolutely. And I'll send you a password on Tuesday.
Okay,
Tuesday. Okay.
sounds good.
Okay.
Thank
Yep.
you.
Okay. Yep. Yep. Absolutely.
So the final practice then
Mm.
comes out tomorrow, that doesn't have any long answers, right? Any essay
Right,
questions.
yeah, it'll have the essay questions. It will have the essay questions. I think somewhere in some slides, I might have said something wrong, but it will have the essay questions. So you'll see the whole thing. It'll be like, oh, okay, this is what we're doing. It'll be pretty similar to that
Okay,
when we take the final test.
okay, it'll be like roughly similar.
Yeah, yeah,
And
same
then-
kind of thing, same concepts, pretty similar.
For the homeworks, we need 7 out of 9, right?
Yes,
Seven out
seven
of
good
9.
ones out of 9, yeah.
And then the optional labs, those, I see the due date is for like Sunday. Is that just an error?
Probably. I meant to set those things to like Tuesday so that you have all the way. That just gives me time to grade them by the end of the
Okay.
week. But I'll be pretty flexible on that.
Okay.
The only thing I'm trying to protect, it hasn't ever really happened, but if everybody did all of them at the
Yeah.
end, I'd be like, completely swamped. So yeah.
Yeah.
So
Okay.
yeah.
I just might
Okay.
do like 1 or 2 of those.
Okay. All right. Cool. All right.
Thank you.
Very good. Very good.
Wait, what Friday are the exam grades coming?
What day will they come?
No, what Friday? Or what day? Like. 'cause
Oh,
if I-
when will I know? When will you know what you
Yeah.
got on the exam?
Yeah, cause I don't wanna like plan to do it like Friday night and then like the grades are already back, so I can't do it. Then I got a 0, you know?
Oh, no,
Just
no,
for sure.
no, it's not gonna be like that. Like,
Okay,
if
okay.
you do it after the answers are posted, it just means it's gonna take me longer to grade
Okay.
it. So,
Alright,
so
like,
you,
they're not gonna be, so obviously the answers aren't gonna be posted anywhere, it's just gonna be like returning the grade.
yeah, yes, right. Yeah,
Okay,
you're
so-
not gonna see the answers unless
Okay.
you do your test.
Okay, right,
Yeah,
right.
exactly. Yeah.
No, cause I'm just making sure
Yeah.
And like,
Yeah.
I don't accidentally end up in a situation where I'm like,
No.
well, you know what, I'm gonna cheat. You know, I take this
I
opportunity.
think the only thing you could do is like call up all your friends and say,
Yeah.
although as I recall, I forgot to give you the password last year and you
Yeah.
put the password.
Yeah.
I was very happy that you were.
Yeah,
able
'cause
to,
I-
so.
I just like, I think I sent like an email to everyone in the class. I was like,
Yeah.
hey, what's the password?
Yeah, I'm so glad that
Yeah.
you did that. Yeah, that was fine. Yeah,
Yeah,
I
I
feel
think-
bad about that.
I
but-
think I used like the announcement system or
Yeah,
something.
good for
crazy.
you. Yeah, very
Yeah,
sad.
yeah, really
Yeah.
use the announcement system. I'll be like, is there any answer key? I'm actually a TA.
Well, I was surprised that people were still on email at that time because usually after there,
know.
they were probably like the last thing they wanted to do was be thinking about school. But,
Yeah.
but
And,
yeah,
like,
I'll get that out to you.
anyway,
Yeah,
Yeah, I just wanna
on
just wanna
Tuesday.
like figure out how to plan my
Yeah,
whole test.
yeah.
You know,
So yeah, I'd say
probably like
you
Tuesday,
you
Thursday.
yeah, and
Yeah.
yeah, and look at what the problem is tomorrow, and then maybe rough out some ideas, in code for the exam week. So,
Okay.
yeah.
Yeah, that sounds good.
Good.
Yeah.
All right.
Also I have a question.
Mm-hmm.
Is there a way to when you have a thread doing something, is there a way to then just change the thread's input or something?
Oh,
Like after it returns a value, is there a way to do that?
not unless you do it through shared memory, and then you'd need to be done via a mutex kind of thing.
Okay.
Yeah.
Alright.
Or you could be tricky and one of its arguments could be a function pointer. And you call it a function and it returns a value to the worker function. So that could
Okay.
be tricky.
That sounds good.
So,
Yeah,
yeah.
I'm just because I wanna alright. There's this math problem that I've been thinking about
Mhm.
where it's you just no, it's just kind of vast. The last time I tried to do it, it got stuck on one of the inputs.
Oh, okay.
So
Hmm.
well, there's no way to do this linearly,
Right.
single
Yeah.
threaded,
Yeah, right. Yeah.
most
Yeah.
programming.
Yeah.
You
Yeah.
know,
Oh, that would be
And
fun.
and I was like, okay, it's if there was a way to just make a function that it's multi-threaded, but once this thing is once this one is done with this input,
Yeah.
it could move it over to the next input.
Yeah, of course.
Yeah.
Yeah, I mean, the function would have to return that value to some stored place in memory, right? So, but that's not too hard. You could have like
No, I know.
a mutex where you have to collect information. That's
Yeah.
But yeah,
I think of using static things, but I feel like that could get messed up because I feel because you can't just say you can't start something and say okay, just for this thread
yeah,
statically allocate this.
Yeah.
It should be statically allocated for everything, right?
yeah, yeah. I mean, if you statically allocate something in a class, think of like the factory scenario. It's like you're just creating global memory. That's what you're doing.
Yeah,
So it's as well as-
so you can't say so you can't create an instance of something and then say static int num or whatever, and you can't it would just update for every instance you make of the class, right?
Yeah, yes. Well, if it's static, yeah. I mean, well, it would be at the factory, and you have all these instances, and that kind of activity. But it really is just like global data. It's
I'm just trying to figure out how you can solve this problem.
I mean, is it if it's really the case that is it a one step or a multiple steps that you do?
Well, I mean, it's just checking if it's just producing larger and larger numbers, and then checking if they're prime.
Oh, okay,
And then,
cool.
I just I just wanna do that, but then just check when once this is done with checking for I don't know just whatever blah blah, and like
That's what
because
I
like
just
like I'm like if
when
it's
he
prime
just and I
turns in,
1500.
then I want to just like then move on to like a next number
Yeah,
and slowly like
Yeah.
fill out this map.
Yeah.
You know?
Yeah.
So
he's
you
like,
could-
oh yeah, those
you
are all this.
You could have any structure you want.
Once
It
the
could be a
finals is like,
vector
right.
Yeah.
that's global.
Yeah, he left like.
And then you have your worker functions where they're just, they get the lock
Yeah.
and they, check something, add something, delete something, release the lock. And then this is gonna grab that. Now, the problem is that
2 semesters ago when I took it.
while this is accessing all the other worker functions are waiting
Yeah.
because you got the lock.
And
But-
I took pictures of it and then.
If most of the work happen, like what's the heavy lifting? Is it the math or is it
It's just like iterating through like different numbers.
Oh, okay.
I'm turning it if it's prime, but like
Okay.
but most of the work is like is done by just like because I don't know, I tried to do it like I think it was like n equals
Yeah.
5,
Uh-huh.
you know, because it's first factorial. You add 1, and then if it's prime, you return it. But if it's not prime, you just multiply by 5 again. Then
Okay.
That's
It's
like
not
the one-
recursive.
I don't think it's recursive. But like I have never been able to like get an output for it. So I was thinking like, well, I mean, I could just do like I can just have like 4 threads or something, and like they can like work something out to like a larger value.
Yeah.
But then like while still like chugging along like figuring out like this or whatever,
Yeah.
then like you know what I mean? Like
Yeah,
just
yeah. It'd be interesting to see. I mean, especially on these computers, like you have a lot of threads and a lot of cores.
Yeah.
that
I just
You're not normally taking advantage of. If those things can happen in parallel, then
problem.
yeah. Because if they're using just
And that's what I
implicit
mean, like,
number
actually, like,
counting,
very-
like if they had to
Simple
read,
fine
if
examples,
all these
like,
threads
hey,
were trying to
okay,
read
2
from
plus
this
2, okay, so
all
here
at
it
the
is.
same
And
time,
that,
it
you know,
probably
and
wouldn't
something
value
different,
much.
and if you have
what if there was like what if there was like a thread with the
it's just
thread?
first I didn't understand.
Well,
Translate
threads can
Polish
launch
and
threads.
really
That's
Polish.
no.
Okay,
definitely do
but
that.
it's so sweet, my name- my
That's
name-
yeah,
I-
that
I-
that would be
not gonna fly like
Yeah, no.
war.
No, I
It's
just
like,
think no, I just feel like
any
because I
language,
wanted-
so like
because I
it's
don't want to just,
yeah,
like,
and then you like
do
I'm
that and
trying
then,
to look for
once it's
definition.
done,
And I'm
doing
like,
that, it's just like,
I don't
okay,
know
I'm
how
done,
to
just
force some definition
only
stuff.
this
I
one
don't know. Like,
Yeah.
just left
you're
and
going like
they'll just go on
yeah,
forever.
literally.
Like I want to just be able to
like
like
half
say,
the
okay,
problem.
like,
and like you just can't do it.
now that we're
Because,
doing
like,
this,
12 other
now
credits.
that we're doing
you're like,
this,
okay, I can't spend
work
like
on a
3
larger
hours
number.
on one
Yeah.
problem.
like slowly just like
Because then like
build out like
I don't-
I guess it's like a vector, but
Good luck, Jess. Thank you. You too. When's your test? Or are you all done?
It's good. What's
We
the
have
next
one more thing to do
Right?
here, but
Like
it's
most of the
some
things.
unknown group assignment. She's not giving us any details.
Yeah.
Those mysterious group assignments.
Indeed.
Yeah.
All right. Good luck. I'll see you.
You gotta finalize, right?
Yeah. 3 next week. So, yeah.
Gotcha. Like actual final, not
Act-
just.
Oh yeah. Yeah. Actual.
All right, good luck to you, student.
Okay. Thank you. Yeah.
yeah, it's just I don't know, I just
You should. You know what you should do? You should just
But
put it in one thread.
okay.
Like get the whole math problem working in one thread that you launch.
yeah.
Like that's step A. But once you do that, like, your mind will probably be like, oh, I'll just create another thing over here. It's a lot easier once you get it in one thread.
No, I know. I'm just it's like I have been thinking about it ever since we did Pride. I was like, I wonder if I could.
It's pretty cool.
You know.
Threads are really cool. The one I'm working on right now is because I wanna send Morse code through a laser, but I want to test it in software first. So I'm gonna have a thread that is laser, and I have a Boolean bit on or off. So the laser is gonna be sending Morse code like dot, dash, dot. So it's just gonna be on, off in a thread as fast as it can. And then there's gonna be another thread over here watching that and trying to interpret what letter it just said. And I almost have it working. This is really close.
No.
But you couldn't do that any other way without having multiple threads.
Yeah, I got some.
So it's really,
Yeah, but when you need like
Yeah, Steve.
I mean like
Like that.
pairs of
Okay,
Booleans,
yes. Oh, yeah, that would be.
you know,
France
it's like,
is still pretty
it's like
expensive, but
off,
if you're
it's
like,
like, feel
like
like
Czech Republic,
you
and
need
then
to
you can
off,
ski for a
off,
week,
off for like,
and like even
a
if you
space, you know?
count the-
Well, yeah,
it-
Morse
it's
code
cheaper
does
than-
have
yeah.
a very strict rule. It's like,
Or like,
Or even like
you have to have at
$100
least
very
a
well,
3
yeah.
gap. So this is a 1 gap, a 1
Yeah, I went
dot,
there this season.
dash is 3.
February, and
and then the gaps
I was like, I can't
have to
afford
be
it. That's very-
off.
I'm just very-
So you're gonna be,
Yeah.
so this has to
Yeah.
be checking timing as well as
Yeah.
high low state, so.
you know, I'm just trying to think about like, because I don't really understand
In $400.
how
Yeah.
it differentiates, like, I mean, are there any Morse code letters that are very long?
Yeah, I think the longest
Like
one
one
is
gram
5
to
dashes or
2
something like that, yeah.
Okay, but like, how does it know? Understand that it's like 5 dash, not just like 1 dash.
Oh,
You know what I mean?
because the gap after is,
Sir, see you on
see you
Tuesday.
later, all right.
Uh,
So the gap after every letter has to be
right?
3 wide. So,
Okay.
so, and it has to be low, like off. So if this Boolean is off for like, let's say 3 seconds, that's like
Yeah.
way slower than it needs to be.
Yeah.
If this was a 1 second dot, then every gap would be 3 seconds. It'd be like, oh, that's the end of a letter.
Okay, okay.
So, yeah, and then the end of a word is 7 gap.
Oh man,
So, yeah.
no.
But to
That's
make
weird.
it go faster, you just shrink the size of the dot down to like,
A bit.
yeah, so, well, in terms of time, the fastest Morse code operators as humans can do 60 words a minute, which is, I think it's like every dot is like, I don't know, it's a fraction of a second. Like, so, you know, they can type that fast and hear that fast, but any faster than that, humans can't really do it. But
Yeah.
computers can, so.
No, no.
Yeah, I
Yeah,
want to
like-
see if I can send music through a laser. Send it to another device and have it sort of
Yeah.
reinterpret it. So
No. Yeah, 'cause you can probably like get like a WAV file or something.
Yeah.
Into like raw
yeah,
bits or I don't know.
yeah,
I don't
yeah.
know how you would do that though, because it's not that easy, you know? You know, cause like, I don't know, I mean it's hard to like just get something like an MP3 into like just binary.
Oh
I
yeah,
guess
yeah,
you can do it, but like, I
Yeah.
don't know, it's like, you know, waves are so complicated.
yeah,
You know,
yeah,
like I've been
yeah. I'd probably create my own.
Yeah, I've been trying to edit music, Ableton, and
Mhm.
you know,
What is it called?
yeah, Ableton Live.
I think I've heard of that. Yeah,
Yeah,
yeah.
and it's like, I don't know, it's a very weird program because like,
Yeah.
because if you import music, you could like, you have to like put it up, but like sometimes you don't always understand like, oh, is there recording me?
No, we stopped recording.